Log properties is how you will learn it in Algebra 2. Log function manipulation is kind of how it's presented in this lesson here. Okay, let's look at these log properties that are going to be really important to you. They're written in their variable form, and then there are good little examples underneath. So this is called the product property. And it says if you have a log of a product, two things that are being multiplied together. Let me zoom in just a tad. A logarithm of a property, you can do what we call expand that out into two different logs that are being added together. So stare at this for just a second. Log base b of x times y can be expanded out into log base b of x plus log base b of y. And here's an example right underneath here with actual numbers in it. Log base 2 of 5x. 5x is a product, two things being multiplied together. That expands out into addition. So multiplication expands into addition. Now you also have to know that going backwards. Sometimes your job, especially on 5.13, the day that I'm gone and you're kind of teaching yourself, this is really important. You might have two logarithms that are being added together and you need to know, hey, I can shrink that down into a single log of a product. So you've got to know this forwards and backwards. So multiplication and addition go together, whether you're going to expand out multiplication into addition or shrink up addition into multiplication. This same thing applies to division and subtraction. Those kind of naturally go together in math, division and subtraction. If you have a log of a quotient or a fraction or two things that are being divided, one thing's dividing the other, then you can expand that out into two logarithms with subtraction. And here's an example. Log base 3 of y divided by 4 can be expanded out into two logs, log base 3 of y, subtract log base 3 of 4. Notice that the numerator, whatever is on top, is first. We're going to subtract the log of the denominator. When you subtract, order matters, so don't get those confused. This is not the same as log base 3 of 4 minus log base 3 of y. That's incorrect. And then lastly, this really isn't even going to feel like you're doing anything. It's not going to feel like it's one of the properties that you have to memorize. If you have a log of something that's raised to a power, so that's really what this is about, that log base b of x to the power of n, there's a log property that says when you expand that, you just move that exponent to the front, and it becomes the coefficient. And the same works backwards. If you see a coefficient of a logarithm, you are allowed to move it to be the exponent. So here's a really good example. Log base 7 of 3 to the x power is the same thing as moving that x to the front of the log. So those are the three properties we're just going to kind of work with today. Okay. These properties can be used to show that various transformations of log functions can be written in equivalent ways. Example 1 for each of the following. Write an equivalent expression by condensing each expression to a single log. So those words are really important because it tells you you're going to take what's in front of you and then shrink it up into a single logarithm. Your answer should only have the word log one time. So on A, I've got two logs that are being added together. And by the way, this only works if the log bases are the same. So let me make this very clear. If this was a log base 4 added to a log base 7, you could not shrink them. You could not condense them. They have to be the same log base. But what we're going to do here, because it's addition, is condensing that is going to condense it to be a product. The log, same base, 4, of the product of those two arguments, x times y. Usually you'll see some parentheses around the argument just to indicate that the log is being taken of x, y, not just of x or something like that. So that's why the parentheses are there, just to kind of group that all together. And that's all you do. So B, we have log base 3 of 5, subtract log base 3 of z. So that's going to condense down using the quotient property that says if you have two logs that are being subtracted, you can shrink that down into the first argument is going to be the numerator of the quotient. The second argument, which is z, is going to be the denominator of the quotient. And fractions, it's pretty important to put parentheses around it again so that we can read that as the log is being taken of 5 over z. And here we've got 3 in a row, so let's kind of think about this. You need to work your way left to right. So I would just kind of ignore the last one for now and just look at this as log base 10 of x minus log base 10 of 5 and shrink that up first. That would be log base 10 of x over 5 minus log base 10 of x. We've got to keep going because it says to condense to a single logarithm. So my next step would then be to see, okay, there's subtraction still hanging out there, so I'm going to have to now do x divided by 5. I'm going to have to divide that by, excuse me, that should be z at the end. That should be z. And when I write that, it's going to look kind of funky. That's going to be log base 10. Notice I'm not bothering to write that because base 10 is implied, of x over 5 over z. We certainly don't want to leave it like that. And just because I'm out of room, I'm going to work horizontally here. X over 5 over z, there's a cool little trick that says you can just bump that z up into the denominator. That's the exact same thing as log of x over 5z. 5 and the z question are both in the denominator. So I took these 3 logs that were being subtracted and condensed them to a single log. If you feel more comfortable having the 10 there, go for it. It doesn't need to be there. D is the first time we're going to see that last little power property being used here because there's a 3 in front of log base 2 of x. That's the same thing as saying, okay, log base 2 of x cubed minus log base 2 of y. I'm allowed to move the coefficient back to be the exponent. That's the power property. And now it's pretty straightforward for you, I hope. That's going to condense to be log base 2 of subtraction condenses to division. So x cubed over y. And then on the next one, I'm going to go ahead and just know that this is the same thing as log base 7 of a squared minus log base 7 of b to the 5th plus log base 7 of 4. They're all log base 7, so I'm allowed to condense them. I'm allowed to combine them. But again, you have to read left to right. So you must do the division before you do the multiplication. You can't jump over here and combine those first, because that will lead you to a completely different answer. So hopefully you've kind of started to tackle that on your own. That's going to be A over B and then to condense this even further, I'm going to multiply A over B times 4, which is just going to end up being 4 times A over B. Because A over B times 4 is the same thing as having the 4 on top. Oops, and that should be, is that what you were going to tell me, Jaylee? I'm completely missing the squared and the 5th. I apologize. Okay, now that looks good. That one used all 3 log properties in one column. Now, F is so weird. If the the goal is to shrink this down into a single logarithm, how in the world would we do that? Our task is to take the number 2 and change it over into log base 6. So try to follow me here, okay? I'm going to take that 2. I'm going to change that over into a log base 6 of something. That will then allow me to combine these. Now you have to be really good at evaluating logs to know how that's going to turn into 2. Log base 6 of what number would give you 2? In other words, 6 to what? 6 to the second power would give you what? I think I might have botched that when I said that. But it's 6 to what power, or 6 squared would give you what answer? 36. Because if you think about the way that you've worked these before, if I gave you this problem in the past, you would convert that into 6 to what power is 36, and that would give you 2 as your answer. So working backwards can be a little bit tricky. Even I have trouble spitting it out, okay? But it's 6 squared gives you 36. That's where I got the 36 from. It's really strange taking a constant and switching it over into logs. And now we can shrink those up. We can condense them into log base 6 of 36x into a product because they were being added together and they condensed into a product. That one is a weirdo. I bet you can do this next one, this multiple choice question. See if you're comfortable with this. If you have a log that's already condensed, see if you can pick the answer choice of the correct way to expand that out. Probably want to show a little bit of work. There are some answer choices lurking that are a little bit misleading. So I'm getting C. Why is it not B? Why is the 2 not in front of everything? Yes, I think you both said the same things. Because Y is not being squared over here. So you don't want the 2 to apply to that one. Did any of you choose a different answer choice and you want me to explain why it's not it? Because that kind of helps me teach it better. Did anybody get a different answer? Or are you confused by any of that? Okay, go to the back. Really all you've done so far is like Algebra 2 level stuff. This is kind of where we start to look at how it applies in a pre-calculus setting. It says the function f of x is defined as log of 6 times x. And it says that that's a horizontal dilation of the function regular old log of x. G of x is just log of x. It's saying that this is a horizontal dilation. Show that f can also be written as, okay, because pause. The horizontal dilation is because the 6 is right here. So it's been dilated by a factor of what? Not 6. 1/6. Remember how x's are always opposite? So f of x is a dilation of g of x by a factor, a horizontal dilation by a factor of 1/6. Okay, but what we're supposed to do is show that that can also be written as a vertical translation of g. So I promise you we're just going to use log properties to show that f of x can also be written as the g of x function plus some number, because that k that moves a function up or down, we're supposed to show that that log of 6x can also be written this way, log of x plus some number. So here's what that's going to look like. We're going to take log of 6x and we're going to expand that using our log property, our product property, that says that's the same thing as log of 6 plus log of x. What the missing component for a lot of you is going to be, well, which of these becomes the value of k? Here, so here's g of x, right here. That's g of x. It says up there that g of x is log of x. So this actually is something that you could type into your calculator and you would get some kind of decimal value. Now, if this was not a calculator problem, you would just leave this alone. That is k, you guys. Log base 10 of 6, that's k. That's the vertical translation right there. Let's switch it around so that it's g of x first and then plus the k value. So here's g of x plus k. K just happens to be written in log form. That's more exact than if I typed in log base 10 of 6 in the calculator, I'd get like 0.778, okay? But you don't need to do that. This is it. This is showing that we took g of x and we added a constant. So again, the big picture is you have to be able to show that a horizontal dilation can also be written as a vertical translation. Very strange. Change of base property. This is kind of a, you don't see this a lot anymore. This was really used when calculators could only do log base 10. Well, when calculators could only do log base 10 and you had a problem on your paper that said log base 7, you would have to change it into log base 10. That's what this allows you to do. It's really cool. So this is kind of like a little code you're going to have to read here. Notice, if I have log base b of x, I can change that into whatever log base I want. So a is whatever you want. Whatever base you want. I could change it into log base 10. So log base b of x would be the same thing as like log base 10 of x over log base 10 of b. Note, this property illustrates that all logs are vertical dilations of each other. So example 4 is going to be kind of another funky one, and then we'll switch back to an easy problem to wrap up the notes. Okay, f of x is log base 4 of x. G of x is log base 9 of x, so they're in different bases. Show that f is a vertical dilation of g by finding k such that f of x is just some number times g of x. Vertical dilations are when you take the entire function and multiply it by something. Notice the k is not inside, it's on the outside of the function. It's a vertical dilation. And I know this is really kind of difficult to put all this together. So f of x is log base 4 of x. Our job is to just show that log base 4 of x is just a vertical dilation of log base 9 of x. So we're going to use that change of base property to say that if I want to switch it over into log base 9, I'm allowed to do that because g of x is log base 9. But the arguments then are going to be, look at your change of base formula. Okay, x, this original argument is going to go on top, and the original log base is going to become the argument of the bottom. So x is going to be up here, and 4 is going to be down here. because there's just a rule that says you're allowed to do that. Okay, now how in the world does that prove that this is a vertical dilation? You're going to have to follow me here. What I can do is I can kind of split that up and say that that's the same thing as log base 9 of x times 1 over log base 9 of 4. The red fraction and the purple product are the same thing. Because if I put those together, I just have log base 9 of x over log base 9 of 4. Yes? Just because this says when you change your base, that the original argument goes on top and the original log base goes on the bottom. Okay, we've basically arrived at the answer because here's g of x, just like I modeled it for you up there in example 3, that's g of x, there's log base 9 of x, multiplied by something, multiplied by, this is going to be your k. You could type that all into the calculator and you'd get like 1.585 just because I've done it before, okay? So k would just be 1.585. Look, k times g of x times k. So that's the answer right there. We just have shown that f is a vertical dilation of g. Now let's do something easy. I don't know why he decided to write this in 2.12 notes when we've already talked about this enough that you already know this. Log base e is called natural logarithm. I mean, we've needed to know that this whole time. You already know that. Log properties apply to natural logarithms, so you can do this probably without my help. Which of the following expression is equivalent to 3 natural log x minus 4 natural log y? Use your power property to move that 3 to be the exponent and that 4 back to be the exponent. And then use the quotient property because they're subtracted to condense that into the natural log of x cubed over y to the 4th. So that's going to be A. Okay. Examples 3 and 4 are by far the most difficult part of the lesson. It's very abstract, and I understand that as I teach it. It's just kind of a weird thing.